Hello everyone, I'm Sahadev Bharat and I'm going to be presenting the Physics 2211 Lab 4 and this is around oscillations. So the introduction is simple. We want to investigate the motion of an object hooked to a spring with the mass oscillating in an arc below. We shall first analyze our actual experiment given by Dr. Greco using the tracker, and then we will have our coding part where we try and match the actual experiment. So the fundamental laws involved are simple. We have the universal gravitational formula. We then have Newton's first law, which says that an object will remain at rest or in motion at a constant speed unless an external force acts upon it. Newton's second law, which says that the acceleration of an object depends on its mass and force applied. And then Hooke's law, which states that the force applied F equals a constant k times the displacement or change in length x. So these are the other laws. We have the energy principle, which is the conservation of energy, which states that the energy cannot be created nor destroyed, which is delta E is equal to Q plus W. This is the total energy, which is kinetic energy plus spring energy plus gravitational energy. These are the three formulas: half mv squared, mg delta y, and half ks squared. And these are the other formulas involved as well, which is the universal gravitational formula minus g m1 m2 by r hat, and then Newton's first law, Newton's second law, and obviously Hooke's law as well. So now if you look at our main setup, we have the experiment which was produced by Dr. Greco, and we imported that into Tracker and analyzed it. We also have our own theoretical model which was supposed to match the experiment. We use a multitude of formulas all from the previous slides, and the initial conditions are simple. Our ball starts at this position. We have an initial velocity as such. We have time, which is 0.760 seconds, and our delta t, which is 1 by 210 some hertz thingy. Then we have our preview and methodology. We have the system, which is the object of mass m, spring, and the earth. There's nothing in the surroundings as everything acts on the object m. Then we have the mass of the object, which is 0.402. I calculated this using Dr. Greco's video. We have the spring constant k, which is 6.83 newtons per meter. The relaxed length L naught, which is 0.123 meter. And gravitational, that's supposed to be minus 9.8, my bad. Then, after the actual experiment, we realized that the model and the experiment had quite similar data and were off only due to some technical errors, which was on my part and some in the video as well. So now let's look at our tracker analysis. So as you can see, the tracker is constantly tracking the data. We have our t of x and t of y graphs being plotted in this side. We also have our entire x and y, which is what we use for this .csv file. And now, if we look at our code-based items, so these are initial properties. Mass was found to be 0.402. The position, velocity, time, which was also on the previous slides. Gravity, k of s, L naught. And these are formulae. L is equal to ball dot position minus spring dot position. L hat, s. Then these are kinetic energy, gravitational potential energy, and spring potential energy, along with the total energy formula. These are all derived earlier. And then let's look at our actual calculation loop. 9.497, this is the final value in the actual tracker data. Then we have our initial energies. We have the gravitational force, which is minus mg. We have our spring force, which is minus ks, s times L hat. We have the net force, velocity, position, which is from Newton's second law. We have the updates, and then we have the actual energy calculations here in these 8 lines. So if we look at our data analysis, this is the x versus y graph. So our x, you can see, is quite accurate, right? And then our y is slightly off, but that's due to some errors, which I'll show later in the slide. But as you can see, there is very less discrepancy in the data, and they actually do quite match. So now errors. So it is possible that I made an error in calibrating the tracker data for the actual experiment video, which is what Dr. Greco gave. Then there's a possible coding error on my end, which is also possible. Then in reality, there are also other forces which act on the spring of Dr. Greco, such as like the damping force, which we've not accounted for in our actual glow script code. So these are just some of the possible errors. And then is the energy principle maintained? Yes, the energy principle is satisfied. As you can see, the red, green, and blue always cancel out, and the orange is always a straight line. So the total energy is clearly zero by this graph. And even though the graph shows multiple, like green, red, and blue, orange, 4 different types of data, the delta A is the one we only care about, which is a straight line in the middle, which says that it's always zero at all times. And then the oscillation, the x versus y. So after some calculations, we determined that the spring constant in x is slightly different than that of this in y direction. 6.83 for k of x and 6.02 for k of y. And as you can see, the reason for the discrepancy in the y data was because we used the actual 6.83 rather than 6.02, which is why the y graph is slightly different. So this is just a minor difference in the data and does not make massive differences in the actual experiment. So if we now try and observe our results, from the above lab we can accurately say that the model matches the experiment quite accurately. Any issues in the matching of the data is primarily due to human errors on my end or the tracking error, and overall this shows the matching of trajectory of a spring and the model. So thanks a lot for watching my video and hope you all enjoyed it.